Lesson 7, Example 6. Looking at what we're presented with, what would you think the most strategic method for solving this system of equations might be? I think solving using substitution is the best method here because this second equation, again, is already solved for y. So I'm going to take what y is equal to and plug it in for y in the first equation. So that's going to give me 10x minus 5. And then I'm going to leave room to plug in what y is equal to here. So I'm going to plug in 2x minus 6. So that gives me 10x minus 10x plus 30 equals 30. And something very interesting happens next. 10x minus 10x leaves no x's. And so we're left with 30 equals 30. So this has not happened in any of our examples before. What happened, though, is our variable actually canceled out. And we were left with a true statement. So it's important that you go ahead and finish this even though you see that the variable is going to cancel out, because what happens is whether this is a true or a false statement here will determine your solution. So if it is a true statement, then what that means is this solution has infinitely many, this system has infinitely many solutions. But I mentioned in a previous example that you need to be a little more specific about where those solutions are, because it's not every single ordered pair in the coordinate plane. The solutions must satisfy the equation y equals 2x minus 6. So remember, when you have infinitely many solutions, this is a consistent dependent system. Now, if I were to graph this, do you remember what the graph is going to look like? Well, let's look and see. If I were going to graph y equals 2x minus 6, we'll call this equation 2. Then remember, the slope is the number in front of x, which is 2, which we can think of as 2 over 1, which tells us the lines rise over run, and the y-intercept is negative 6. So let me go ahead and draw some tick marks on this coordinate plane. So if you remember how to graph a line, we're going to go down 6 on the y-axis, 1, 2, 3, 4, 5, 6, and we're going to plot a point. From that, we're going to walk out the slope, so we're going to go up 2 and over 1, up 2 more and over 1. So this line looks like this. So we'll call this line 2. Now to graph line 1, we need to solve it for y. So to solve equation 1 for y, we would have 10x minus 5y equals 30. If I subtract 10x from both sides, that's going to give me negative 5y equals negative 10x plus 30. And then if I divide both sides by negative 5, something interesting happens. So on the left, we're left with y. Negative 10 divided by negative 5 is 2x. 30 divided by 6 is negative 6. So look what happened. Line 1 and line 2 end up being the same line. Or another way to think about it is they're overlapping. So if you remember, that's what happens when you have infinitely many solutions, and the ordered pairs that lie on that line are where the solutions live. This is the last example in Lesson 7, and it looks a little intimidating because of all the fractions. But one trick that we're going to learn that will prove helpful to us is to get rid of fractions. You can multiply by the common denominator. So that's what I'm going to do to make this system a little less intimidating. So if I call this equation 1 and this equation 2, if I look at equation 1 and I look at just the denominators, the fractions all have a denominator of 3. So watch what happens if I multiply this equation by 3. Now, if I'm multiplying the whole equation, I've got to multiply everything. So this will give me 3x plus, and here these 3's cancel, so that just makes it 5y. And then these 3's cancel, which will make it just 1. That's not too bad now. Now, if I look at equation 2, what do you think I would multiply equation 2 by to get rid of the fractions? That's right. I'm going to take equation 2 and multiply it by 2. So I'm going to have 2 times 3/2 x plus 5/2 y equals 2. So I need to multiply everything by 2 to keep it equal. So these 2's are going to cancel, which leaves me with 3x, plus these 2's are going to cancel, which will leave me with 5y. And then this only has a 1 on the bottom, so the 2's don't cancel, so 2 times 2 is 4. Now, I would say that this system lends itself to elimination, or another name for that is addition, remember, because neither equation is solved for one of the variables, and we don't have the coefficient of 1 on either of the variables. So I'm going to take equation 2, I'm going to multiply it times -1 now, so that I'll have opposite signs. So if I bring that over here, that's going to give me -3x, -1 times 3x, -1 times 5y gives me -5y, and -1 times 4 will set it equal to -4. Now I'm going to add these two equations together, and something interesting happens again. Now, it won't happen all the time with elimination, but sometimes it does. So the 3x's cancel, but the 5y's also cancel. So I'm left with nothing on the left-hand side, and we represent nothing with 0. Now, it is important that you actually bring this down to this step, because remember, when the variable cancels out, what determines your solution is whether you're left with a true or a false statement. So 1 minus 4 is -3, and 0 does not equal -3, so that is false. So can you guess what the answer is? The answer to this then would be no solution. Do you remember what the graph looks like? If we were to graph this, they would be parallel lines. So let's take a minute to do that. So I'm going to take 3x plus 5y equals 1. That's my first line. And 3x plus 5y equals 4. That was my second line. So that's what I got when I multiplied by 3. And that's what I got when I multiplied this equation by 3. And I'm going to solve these equations for y. So for the first one, I'm going to subtract 3x from both sides, which will give me 5y equals negative 3x plus 1. And then if I divide both sides by 5, that's going to give me y equals negative 3/5 x plus 1/5. So for equation 2, I'm going to subtract 3x from both sides again. So that's going to give me negative 3x plus 4. And then if I divide both sides by 5, I'm going to get y equals negative 3/5 x plus 4/5. Now, hopefully, you're starting to recognize the fact that these lines have something in common. If we look at the slope of both of these lines, notice, that the slopes are the same. And if you remember back from lesson 6, I think, lines that have the same or equal slopes are parallel. But let's go ahead and finish this out by graphing. So I'm going to go ahead and put some lines on here. So 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. All right, so if I'm going to graph the first line, remember that my slope is negative 3/5 and my y-intercept is 1/5. So I'm going to go up just a little bit on the y-axis. That's 1/5. And then from there, I'm going to go down 3, 1, 2, 3, and over 5. Whoop, I didn't do enough lines, did I? 1, 2, 3, 4, 5. Now let me extend my coordinate plane just a little bit more. Sorry about that. 1, 2, 3, 4, 5. Okay, so this is the first line, the graph of the first line. Notice that that line is falling if you read it from left to right, which makes sense, hopefully, because the slope is negative. Now to graph the second line, the slope again is negative 3/5, but this time the y-intercept is not 1/5, it's 4/5. So I'm going to go up a little bit higher on the y-axis, so that would be 4/5. From there, though, I'm going to go down 3, 1, 2, 3, and over 5 again. So we see, sorry, I do not draw straight lines very well. So when we graph these, we see that they are, in fact, parallel because their slopes are equal, which means they'll never intersect, which means there is no solution. And if you remember, we call this system inconsistent. So just to round out this video, let's go back to where we were showing the 3 things that could happen, and let's make a note here. If the variables cancel out completely, and A, you are left with a true statement, you have infinitely many solutions. If it is a false statement,